Hi everyone, welcome back to more cell concentration stuff in Chapter 11, Chem 2C. Today we're going to be talking about the Nernst equation. I'm going to get right into it. So first of all, what is the Nernst equation normally used for? It's used to calculate. So you can either calculate the E, which I'll get to, Ecell. It's different from E cell, the one with the degree sign. Ecell, and it's also used to calculate K, Q, different concentrations, and I think that's it. Those are like the main things that you can use. All right, something here. Those are the main things that you can use the Nernst equation for. So if you remember from previous videos or previous chapters in the class, there is a difference between E and regular E, and for this E is for standard conditions, which is 25 degrees Celsius and 1 molar. But then if the molarity of a cation or a reaction in the in the galvanic cells change, then let's say it becomes 0.5 molars instead of 1 molar, then it's Ecell instead. You can't have the standard reduction potential when it's not in standard conditions. And now the Nernst equation, what it looks something like this, where it tells you the E, which is different from the E naught, equals to the E naught minus 0.0591 over N, and then log Q. But something important to remember is that there are two different forms of the Nernst equation. So there's this one with the log, and then another one that looks like this. Practically the same thing. E is equal to E naught minus, but then the number changes, it becomes 0.0257. This is volts, by the way. It doesn't really matter. Over N, not ln, not log. It changes to ln this time, but then it's still Q. And there's a bunch of algebra that goes into the difference or why there's ln and log, but I'm not going to get into that in this video. And for this equation, the different things so E obviously means the cell potential, not at standard conditions. E naught is the standard conditions of the cell potential. This is just a number. N equals to the moles of electrons transferred, and then Q is equal to the reaction quotient, which, if you don't remember, is just the concentration of the products over the concentration of the reactants. And now I'm going to get right into a problem that would ask you to make use of this Nernst equation. So over here is a quick and easy question that I generated from ChatGPT, asking, or one that requires you using the Nernst equation. I'm going to be using this one up here. Just, I don't know, it was the first one I wrote down. So I'm not saying one's better than the other, I'm just deciding to use that one. So I'm going to try to be quick in all these problems because I'm trying to cram a bunch of problems into one video and I don't want it to be too long. So first, the question here is, we're looking for the E. So this is a sort of simpler type of problem where you just plug in what each of the things is while you're looking for E, not E naught. So over here, before we can start plugging things into E, we have to find the different variables. So like the E naught, the N, and then the Q to plug into the equation. So first of all, the E, this is relatively easy to do as well. You just look at it, it's the cathode minus the anode. And then over here, they already told you which is the cathode and which is the anode. But if these were like canceled out and you weren't given and you were told to find which is the cathode and which is the anode, the cathode is, since it's based off the standard reduction potential, remember, the higher the reduction potential, that means this element, this reaction wants to be reduced more than this one since it's higher than this one. So we do the higher one minus the lower one, which is over here. This is higher, this is lower, do this minus this to get the total standard reduction potential. Or we use the formula cathode versus anode, but it's the same thing. It's basically telling you The cathode wants to be reduced more, which is why I use the higher one, minus the one that wants to be reduced less is the anode, minus the anode, which is the lower one. And over here, if we do 0.337 minus negative 0.763, we get 1.10 volts. And now we look for the N. The N is just the number of moles of electrons transferring. So as you can see over here, they both have 2. So if you were to combine these equations, you don't have to multiply by 2, since they both have 2 and they both cancel out. The electrons both have a coefficient of 2. So over here, the N is just 2. And then the kill is the product over the reactants. And as a shortcut, I know that the one getting oxidized is a product. So the anode is usually the product. So it's which is the anode? The zinc. It's gonna be this over this. But then I'm gonna show you how I figured it out, just in case you couldn't do it in your head as well. So what I do is I write out the full equation. So I write zinc plus, since this is the anode, I know it's gonna be, or you just look at it here, combine the reactants. So these are the reactants, and then these are the products. So you combine these reactants, and it's zinc plus Cu2 plus goes to, and then remember the E cancels out, and you're left with zinc 2 plus plus copper solid. And now, since you have this, you can see that the product is, these are the product, this is the product. So that's why this is going to be the product, the anode. The anode is going to be the product, while this is a reactant on the other side of this arrow. So that means the cathode is going to be the reactant. So, and for Q is always going to be product over reactants. So we can just plug it straight in right now. I'm going to erase this. And then we put the product, which is 0.10 molars divided by the reactant, which is 1.0 times 10 to the negative 3, also molar as well. And when you plug this into the calculator, you get the kill is 100. And now we just put it into the equation. E is equal to, we put in 1.10, plus minus 0.0591 over 2 times the log of 100, and we get E. Now next up, I'm going to be doing a problem where you have to find one of the concentrations. So up here, the kills, let's say you have to find this one or the product concentration. And I'm also going to try to do that quickly for time measures. So for this one, we read it quickly. The standard hydrogen. So one of the reactants, or what I say, one of the cells is hydrogen, and then the other one's copper. In the reduction potential of hydrogen, since that's the standard element, it's 0, and copper's is where is it? 0.34. So since copper has a higher reduction, it's going to be on the right, which is what they say here, cathode, while the hydrogen's on the left. But as we go on, we look for more stuff. They told us this, so we can easily find the E0 now, which we're going to do. So the Ecell is just going to be the cathode minus the anode, and the cathode is the copper, which we already figured out is 0.34, since it has the higher reduction potential, minus the reduction potential of hydrogen is just 0. So the overall standard reduction potential is 0.34 volts. And now we find the N, but it's already given right here, which is, it's 2. And then, this is the Nernst equation that we're using up here, but we have the E naught, which is the standard cell potential, and then we also have the E, which is the concentration based cell potential. But what we're looking for is the kill. We don't have the kill, but we have one part of the kill, which means we can find the other part of the kill over here. And then we have the E, it's given to us, it's already measured, 0.12 0.22V. So this is a kind of question where you're going to be looking for the Q, or part of the Q, since we have we're supposed to be given one of the concentrations, if I can find it. The copper is the unknown concentration. Well, since we weren't given another concentration, you can read the question again. It says standard hydrogen. Remember what I told you about chem? Things about chem, a lot of things about chem. When it says standard, it means it's at 25 degrees Celsius or 1 moles. So that means we do already have the concentration of hydrogen, which if we write out the equation, so when you write it, this is a copper equation, as we can see here. The cation is on the reactant side, so we don't have to do the hydrogen part because we know the hydrogen part is an anode, and remember, we know the anode is going to be on the product side. So over here, we're going to have the H part over here on the product side. So that means the 1 goes on top, since it's the product, over the copper goes on the bottom. But we don't know what the copper concentration is, which is what we are looking for. Then we write out the whole Nernst equation again. Let me write it out here. E is equal to E naught minus 0.0591 over N times log of Q. And we don't know the Q, so we plug everything that we do know in. 0.22 volts is equal to, the standard is 0.34 volts minus 0.0591, and we know that N is also equal to 2 over 2 times log of 1 over question mark, what we're looking for. Yeah. And now we just do algebra. We do the easiest thing we can do, subtract 0.34 from both sides. And when we do that, we get negative 0.12, negative 0.12 is equal to negative 0.0591 over N times the log of 1 over question mark. And now we move, since this is multiplied, we can just divide this whole thing, this part, by this side, and when we divide, we just flip it to the other side. So it becomes N times negative 0.12 over negative 0.0591. And then we divide these two numbers, negative 0.12 and negative 0.591. And actually, we know the N's too. Forgot to plug that in. We've been known the N's too. Put it 2. So we multiply 2 by, we just multiply these two numbers. 2 times negative 0.12, which is negative 0.24. Negative 0.24. And then we divide these two numbers, and it's equal to the log of 1 over question mark. When we divide these two numbers, we get a positive number, obviously, because the negatives cancel out. And it's 4.061 is equal to the log of 1 over question mark. And now to do the log of, to isolate, to get rid of the log, we just take 10 to the power of both sides, since that's logs. And when we take 10 to the power of both sides, this becomes a large number, so 11,500 and, what I say, 6 is equal to 1 over square root, 1 over question mark. And now to find the question mark, we just flip the two, take both sides to the negative 1. That's easier because it's a reciprocal. And when you take both sides to the negative 1 power, you get question mark is equal to 8.691 times 10 to the negative 5. And you can leave your answer in moles because that's what we're looking for, a concentration. So we just found the concentration of copper 2+ in this reaction. And now for another idea introduction. I'm not going to do a full question on this, but if you remember from a previous video, where we were given two substances, iron here, for example, with different concentrations. I inputted it down here. These two irons both have the same standard cell potential. So when you want to find the Ecell, which is something you can't find if they have different concentrations, because the electrons do transfer with different concentrations. Remember, the equation is E0 minus 0.0591 over n times log of Q. So for this equation, since they both have the same E0, it gets rid of this in the equation, because if they're both, let's say 0.7, they're not, but I'm just saying, you know, the E0, this E standard potential would just be the cathode minus anode, but they're both the same thing. So you just get negative, let's say if it was 0.7, it would be 0.7 minus 0.7 is 0. So this part of the equation would just be 0. And then it will become the Ecell is equal to negative 0.0591. Now I'm going to do this question because it's not that hard. And then you can see they both transfer 2 moles of electron between them over 2 times the log of the product over the reactants. And the products, like I said earlier and also the previous video, the product side is always going to be the side getting oxidized. Right here it goes from 0 to 3, and then 3 to 0 is the side getting reduced is the reactant. So the side lower concentration is the product, and higher concentration is the reactant. Over here, you put it into, when we put it in here, the I'm tripping out a little. The lower concentration is the product, yeah. So it would just be 1.0 molars over 5 mole. And we can just plug this into the calculator and do it. And one thing before I plug into the calculator to know is that another reason for you to remember of why it's the lower over the higher in terms of Q is because this is going to be turn out to be log of 0.2, because 1 over 5 is 0.2, and log of any number less than 1 is a negative number. So we need the Ecell to be positive for it to be a spontaneous reaction, which galvanic cells are. We need this log, the log of the Q, to be a negative answer, which we're going to get if we do log of 0.2. It's going to give us some negative number, like I think this is the actual 6.9. It's going to give us this negative number, which we then multiply to another negative number over here, and negative times negative gives us positive. And we want the Ecell to be positive, which is why when you can get a negative log times a negative thing, you know you're on the right track, which is why the lower should be on top. The lower is a product over the higher is a reactant. And when you plug this into the calculator, you get a positive number here, which is 0.021 approximately volts. And see how it's a lot less than the other volts. Like other volts, we have 0.34 or 0.22, but over here we have 0.021. So same cell, same element cells aren't as efficient. Even if the concentrations are vastly different, it's just not as efficient as well, but there's still a little bit of energy transfer. And then the last concept based on Nernst equation that I'm going to be talking about is something that else you could also trace back to prior Chem. It's about equilibrium and the K. There's a difference between K and Q. So we've been using Q the whole time. Q is the reaction quotient between the product and the reactant. But one thing to know is if the reactant, so Q is just basically an equation at equilibrium. So if someone were to ask you or tell you that the reaction is at equilibrium and to find the K constant, I'm going to show you how to do it. Over here is ChatGPT's explanation, and then this is an example problem of what to do. So over here, this is the regular, oh yeah, by the way, I didn't mention this at the start of this video, but this is how the Nernst equation that I showed you is derived. All this, the rate, the temperature, the moles, and Faraday's constant, but you don't got to know all that. You just have to remember this part of it. And remember, notice how this part, so the equation I've been using this whole time has Q, But then when you use K instead, over here it says the E. So when a reaction or when a cell is at equilibrium, the E becomes 0, which is why you have over here. So E is just going to be equal to positive of this if you're looking for the K. So if the reaction is at equilibrium, the cell potential is 0, and to find the K, you just use the E value. The standard, the standard. So you manipulate the equation to get K alone if you're looking for K, and if you're looking for the standard reduction potential at equilibrium, it's just this. If you can't find the standard reduction potential because you're not given the table or whatever, but you do know the K, you can find the standard reduction potential like that. But most likely you're going to be when they tell you that the cell is at equilibrium, it's usually find the K. That's usually the type of questions involved. And this is an example that ChatGPT also provided for us about how to find the K. So over here, you're given this reaction, and then you're given the standard cell potentials of both of them, which you can use to find the total cell reaction, which is they did over here. And then they did the algebra for it. They got rid of this E from the original equation. They got rid of it. And then they know this, they know that. Oh, and this was K, by the way. And now they're looking for the K. And over here, you can see they have it like this. They manipulated it, just do a bunch of algebra, bring it over to this side. It's equal to this, and then you divide both sides. You multiply this times 2. You move the 2 over to this side, multiply by that. Then move this over to the denominator, divide it by that, and then raise both sides to get to the 10 power to get rid of the log, and you get K. And if you notice, you don't need like Q, you needed the product concentration divided by the reaction concentration. In K, you don't really need that since the product is at equilibrium already. And I think that's most of the type of problems you can get based off the Nernst equation, and hope you understood the Nernst equation after this. Thank you for watching. Make sure to like, subscribe, and comment, and see you later.